In alternating current, the voltage and current do not stay constant like DC. Instead, they oscillate back and forth. To compare this changing energy to a steady DC source, we need a standard measurement known as the root mean square or RMS value. If we apply a peak AC voltage of 10 volts to a heater, it produces less heat than 10 volts of constant DC. This is because the AC signal spends most of its cycle at values lower than its maximum peak. The RMS value is defined as the equivalent DC value that would produce the same amount of heat in a resistor. It represents the effective value of the alternating current, allowing us to perform power calculations easily. To derive RMS, we first square the instantaneous values. This turns all negative portions of the sine wave positive, ensuring that when we average them later, the negative cycles don't simply cancel out the positive ones. Finally, we take the square root to return to the original units of volts or amperes. For a pure sine wave, the math simplifies beautifully. The RMS value is always the peak value divided by the square root of 2. Think of the RMS as the useful part of the wave. While the peak reaches 100%, the effective work done over time is equivalent to roughly 71% of that peak value in a standard resistive load. Phase describes the timing relationship between two waves. In AC circuits containing more than just resistors, the voltage and current often do not reach their peaks at the exact same moment in time. In a purely resistive circuit, like a toaster or incandescent bulb, the voltage and current are in phase. They rise and fall together, meaning the phase angle is zero and power efficiency is at its maximum. Inductors, like motors or transformers, cause the current to lag behind the voltage. Because the inductor resists changes in current, the voltage reaches its peak first, creating a 90-degree phase shift. Capacitors have the opposite effect. They act like storage tanks that fill up quickly, causing the current to lead the voltage. In a purely capacitive circuit, the current peaks 90 degrees before the voltage does. Let's apply this. In North America, the standard wall outlet is 120 volts RMS. To find the actual peak voltage hitting your devices, we multiply 120 by the square root of 2, which equals approximately 170 volts peak. When calculating power, we always use RMS values. If a 46 ohm heater is connected to a 230 volt RMS supply, the power consumed is 1150 watts. Using peak values here would result in an incorrect, inflated power rating. If we observe a 5 millisecond delay between voltage and current in a 60 Hz system, that represents a quarter of a cycle. This translates to a 90-degree phase shift, indicating a reactive load. Engineers use phasor diagrams to simplify these relationships. Instead of drawing waves, we draw rotating vectors. The angle between these vectors represents the phase shift, making complex circuit analysis much easier to visualize. To summarize, RMS values allow us to treat AC like DC for power calculations. Remember that for sine waves, RMS is about 70.7% of the peak, and phase shifts occur when inductors or capacitors are present. Quick question: if your peak voltage is 10 volts, what is the RMS value? If you calculated 10 divided by the square root of 2, you get 7.07 volts. Thank you for learning with us. Generated by Vision Solve AI.